Hi everyone, I'm Alessandro Lenoci from the Hebrew University of Jerusalem, and I'm here to talk about dark matter. And the thing is that I want to already put forward and tell you that I will not explain to you what dark matter is, because this is an answer that is worth a Nobel Prize. So I will try to tell you what I do and how we are trying to tackle this challenge of the dark matter. So when I was a child, I was asking myself questions like, what came before us? What was before humans, before civilization? And I could have become an archaeologist or a paleontologist, but I was attracted to physics. And I started asking myself questions like, what is the history of our universe? And I discovered that cosmology is the discipline that tries to answer this question. And history is taught through key events and key characters. And the way cosmology tells us the history of our universe is through a sort of timeline of key events. We have formation of the first nuclei, atoms, structures, galaxies. And we can ask also, who are the main characters of this story? Well, we surely are there. And we are important because we are made of the same stuff, the same atoms, the same particles that stars and galaxies are made of. So we are surely very important and main characters in the history of the universe. But then there is this guy, some character that we still have to unlock, and it's the dark matter, and we don't know what it is. So when we think about dark matter, we also have to think, how are we going to detect it? Like, what is its importance? And dark matter is actually crucial because without it, we probably would not exist. And this has to do with the way that galaxies form. You see, the way galaxies form is due to the gravitational pull of the dark matter that attracts visible matter into some traps, some gravitational traps, where the visible matter interacts with each other and stars form. And this is how the whole galaxy's picture that we have in mind when we see the universe is there. They are there like flies in a cobweb made of dark matter. And this is what we call, in the jargon, cosmic web. And this is something that we can actually see with our eyes. We can see all these galaxies as dots. This is a sky map that maps the position of each galaxy that we see. And they trace the distribution of dark matter in the universe. So they kind of make the picture of a cobweb. And the result of galaxy formation is that dark matter, it's an envelope of all these galaxies, and we are in one of those galaxies, that surrounds the galaxies, and it's also connected to other halos by these filaments. So what we have in mind is a picture in which our galaxy is completely wrapped in dark matter. So now that I told you why dark matter is important, we try to understand what it is. And we know, at least for now, that dark matter is invisible, so we don't have any evidence of dark matter interacting with visible matter. And maybe it interacts only gravitationally, for what we know. Because it interacts gravitationally, we know that it has to have mass, and this is very important. We know that dark matter is very abundant in the universe. In particular, is 5 times more abundant than us, that is visible matter. And fourth, it's everywhere. So this is crucial because maybe if point 1 is actually not so true, we can try to detect it in a lab. But to detect it in a lab, we kind of have to have an idea of what it is. And here we are completely clueless because we don't know the mass. If we put our ignorance on a line, we can go from super high values of the mass in this unit, the electron volt, or super low, 10 to the minus 22. And from here to here is 50 orders of magnitude. That is 10 with 49 zeros. It's hard to imagine. To give you some references, it's like to go from the mass of an ant to the mass of a virus, to then the mass of an atom, 10 to the 9, and then the mass of a neutrino, which is the smallest and tiniest particle that we have detected so far. What I do in my research is mostly focusing on this part of the parameter space, that is the ultralight regime. And a synonym for ultralight dark matter is wave dark matter. And this is because ultralight dark matter behaves as a wave on astrophysical scales, as opposed to particle dark matter, which it's heavier. So let me step back and explain to you this concept, which is kind of tricky. So in physics, we can describe physical objects in a dual way, particle or wave. And this depends on the length scale that we are probing. Let me give you an example. So if you're swimming at the sea, you're having fun, and then these little drops of water go into your eyes. In that moment, you're experiencing the water as a particle, okay? Then you go on a larger scale, and the water now looks like waves. And what you see here on the Tel Aviv beach is a series of diffraction patterns where you have your wave against the breakwaters. So the things kind of depend on the scale you're looking at. And if we go back to quantum physics or quantum object in general, we can associate to each particle a length scale that represents the size, the length at which we have to look at the phenomena to experience their wave nature. And in particular, the lighter the particle, the longer the wavelength. So the longer the scale at which, the larger the scale at which we will see the effects of the wave nature of matter. Now, let's apply this to dark matter. I told you that I focus on this very light part of parameter space. This actually mirrors in the length scale in some pretty large scales. So if we take 10 to the minus 4 as an example, this corresponds to the size of a human being. Then we can go to lower and lower scales, and we can go to Sun-Earth distance, or even the size of the whole galaxy. We just have to choose the value of the mass here. Now, nature probably chose the mass for us, but what we can do to find what dark matter is to explore all these scales. And what that means is to look at different astrophysical systems. And this is what I do. I try to come up with some possibly smart idea to find the dark matter in all the possible systems that can live here, like a black hole, the sun, and so on. So let me give you an example, kind of like a simple sketch of something that I did in the past. I take the solar system because it's our home, and we know from how we experience dark matter, that is galaxy formation, that our galaxies is in the dark matter halo. And we know that the solar system is also in the galaxy, so the solar system actually travels inside the dark matter halo. And in doing that, it experiences a so-called dark matter wind. This is similar to what we feel when we bike and we feel the wind. The faster we bike, the more wind we feel on our face. Due to the fact that the sun is pretty big and pretty massive, the wind actually falls and gets deflected into a specific point of the orbit of the Earth. And we expect that, that on Earth, on March 1st, we have more dark matter than usual. This is important because experiments look at these differences when they have to discriminate a background from a signal. Now, if we consider wave dark matter, that is, the dark matter is very light, and we plot this overdensity over the year, we see that the pattern is pretty different if we have heavy dark matter or light, that is, wave or particle. And the important thing is that you see here there are some diffraction patterns because the dark matter behaves as a wave, similar to the sea at the Tel Aviv beach. However, what if we cannot detect dark matter? Okay, we go in the lab, we don't see anything because the dark matter does not interact with our experiment, with the stuff that we have in the lab. This I call the darkest of the dark matter scenario. So the dark matter is so dark that you don't see it. However, the wave dark matter can be maybe our only hope to see our dark matter, because all these effects that I told you, the wave nature, they don't depend on actually the coupling between the dark and the visible, so we and the dark matter, but they only depend on how the wave behaves. So if we see some diffraction pattern, if we see some effect in other observables, we can actually discriminate them. So I guess what we should do is to look for the wave signature of dark matter in the sky and keep our eyes open for the future. Thanks.